We use it pretty much every second of every day. But how does the internet actually work? It feels like magic, but it's really not. Behind every single click is this incredible high-speed journey that can circle the globe in just a fraction of a second. So in this explainer, we're going to follow one single piece of data and uncover the invisible architecture that basically runs our modern world.
I mean, really think about it. You click a link and poof, in less time than it takes to blink, a page from a server maybe halfway across the planet just appears on your screen. An entire invisible relay race just took place, and that is exactly what we're going to map out step by step.
So our data packet's global journey starts, well, pretty small actually. The first crucial step happens right where you are, on your local connection, just getting from your click over to your router.
This diagram right here, this is basically the blueprint for all communication. Your computer is the source, the web server you want to reach is the destination, and everything in between, the cables, the Wi-Fi, the routers, that's the channel. This simple concept is the foundation for the entire internet.
Okay, so your request kicks off its journey on what's called a local area network, or a LAN. This is either a physical Ethernet cable plugged into the wall, or what's way more common these days, Wi-Fi, which uses radio waves to connect your device to the router completely wirelessly.
To put it simply, a LAN is just a group of connected devices all under one roof. Think about your phone, your laptop, and maybe a smart TV all connected to your home Wi-Fi. That's a perfect example. It's the little local neighborhood our data has to navigate before it can hit the global internet superhighway.
Okay, so our data packet has left your device and it's made it to your router, which is basically the gateway to the outside world. It's now ready to enter the massive global internet. So the big question is, how does it know where to go?
This really is the core challenge of the internet. It's kind of like trying to mail a letter to one specific person in a city of billions of people, but you don't know their street address. How in the world does your request for a website pinpoint the exact server, maybe thousands of miles away, that holds the data you need?
Well, the answer is the Domain Name System, or DNS. You see, computers don't understand website names like we do. They only understand numbers, specifically IP addresses. DNS is literally the internet's phone book. You type in a name that's easy for us to remember, and it looks up the computer-friendly IP address needed to make the connection.
And this diagram shows the really elegant logic behind that whole naming system. It's a hierarchy. You read it from the most specific thing on the left to the most general on the right. So, Server 1 is the specific machine. It's part of the CS department at the NEC Educational Institution, or EDU. It's just a beautifully organized system for the entire internet.
Okay, so thanks to DNS, our data packet now has the correct IP address. It's been properly addressed and stamped. Now it's time to hand it off to the real workhorses of the internet, routers. Think of them as the traffic cops, directing packets and telling them exactly which way to go next.
Now here's the crazy part. No single router knows the entire path. Instead, it's this massive team effort. When your packet arrives at a router, it makes one simple, lightning-fast decision. What's the very next hop that gets this packet closer to its final destination? Then it just passes it on. This happens over and over and over. A global game of pass the packet that crosses entire continents in milliseconds.
Now, for this whole global game to work, with billions of devices made by thousands of different companies, everyone has to be playing by the same set of rules. In networking, we call these rules protocols.
Protocols govern literally everything: the timing of messages, their size, their format, you name it. This agreed-upon rulebook is what allows a device in Japan to send a packet that a device in Brazil can understand perfectly. It's the universal language that makes a global internet possible.
So for browsing the web, the most famous protocol is HTTP. This is the specific set of rules your web browser uses to ask a server, hey, can you please send me the files for this web page, and for that server to respond with all the right data.
But underneath HTTP, you've got the two real heavy lifters, TCP and IP. Think of it like sending a book in the mail. The IP protocol is like the address you write on each individual box. But the TCP protocol, that's the person who first chops the book into pages, numbers every single page, puts them in the boxes, and then, on the other end, checks to make sure every single page arrived and in the correct order.
Here's a perfect, real-world example of a protocol in action. Ever wonder how your phone instantly gets an IP address when you connect to a new Wi-Fi network? That's a protocol called DHCP. Your computer sends a discover signal,
The server offers an address, your computer requests it, and the server acknowledges. A perfect, automated 4-step handshake, all governed by that protocol.
So, we've followed our little data packet on its incredible journey. Now let's just zoom out for a second and look at the big picture, the digital backbone that makes this all possible.
So yeah, that one tiny click triggered an incredibly fast and complex chain reaction. Your request was translated by DNS, it was sent across your local network, and then it was passed from router to router across the entire globe, with every single step guided by that shared set of rules, the protocols.
So, when you boil it all down, what really makes the internet work? It's these 4 key ingredients, all working together perfectly. You've got a layered architecture, so each part can focus on its own job. You've got specialized hardware, like routers, acting as the traffic cops. You have a common language of protocols, so everyone can talk to each other. And you have a global addressing system, so everyone can be found.
And all of this leaves us with a pretty fascinating question. This incredible system was designed really for computers to talk to other computers, but now we're connecting everything, our cars, our homes, even our coffee makers. So how will this invisible architecture have to evolve for a world where literally everything is online? That right there is the next chapter in this story. Thanks for joining me for this explainer.